All right, hi everyone. Welcome to this section 4.1 video. And in this section, we're going to start our journey of looking at second order or higher differential equations and just learn some preliminary theory of how to find solutions of second order or higher differential equations. So we have quite a few learning objectives for this section. Mainly define homogeneous and non-homogeneous differential equations. We're going to be able to identify linear, independent, or dependent solutions, and also learn or relearn the Wronskian tool. And we're going to define a fundamental set of solutions and get general solutions for homogeneous and non-homogeneous differential equations. And then lastly, verify if sets of solutions form general solutions for homogeneous and non-homogeneous differential equations. Okay, let's look through the introduction and get an idea of what we're going to be talking about for this section. So, through our work in chapter 2, we saw that we can solve a few first-order differential equations by recognizing them as separable, linear, or Bernoulli equations, and then solving them analytically with their various methods. Even though the solutions of these differential equations were in the form of a one-parameter family. So now, as we move towards higher order differential equations, we want to find general solutions to these, where a general solution is a family of solutions that contains all solutions of the differential equation. So transitioning from a one parameter family to a general solution that has a family of solutions of the differential equation. So we're talking about first order, second order, higher order. Let's kind of backtrack a little bit and revisit what first order differential equation is. So back in first order land, here's a differential equation, y prime equals 5y. First order because we have a y prime, just a first derivative. So this is asking which of the following is a solution? So the way we verify a solution is we need to substitute into the differential equation and see if our solution holds true, either left hand equals right side or however you see fit. So let's go ahead and try that out. So y prime is 2e to the 2x with that chain rule. And so we plug in. So this would be 2e to the 2x equals 5 times y, which is e to the 2x. And we get 2e to the 2x equals 5e to the 2x. Those don't match. Those aren't the same functions. Left-hand side doesn't equal the right-hand side. So this is not a solution. So therefore not a solution. Okay, let's go ahead and try some other ones out. So let's look at B. We have y equals sine x. And so we want to take the derivative. So y prime equals cosine x. And so we plug in and we get cosine x equals 5 sine x. Once again, this is no solution. Okay, so pause the video, try out example C and D and see what you come up. Okay, welcome back. So hopefully you tried out problem C and D and saw that example C, we get 0 equals 50, which is not a solution. But for example, D, we actually get a solution. The left-hand side equals the right-hand side when we substitute in the solution with the derivative, and so it's a solution. Okay, so this is us in first order land verifying a solution. So let's take it up a notch. Let's go ahead and move into second order land, and let's see if we can verify some solutions for the second order differential equation. So y double prime minus y equals 0. So which of the following is a solution? Let's look at example A. So it's a second order, that means it's two derivatives. So I need to get two derivatives here. So y prime is just e to the x, y double prime is again just e to the x. So we plug in and we get e to the x minus e to the x equals 0. And so uh, there's a different ways we could do this. I want to move over e to the x to the right-hand side. But yeah, e to the x is a solution. So therefore a solution. Let's look at example B now. So similar, but now we have a negative x in the exponent. So let's go ahead and try that out. A derivative of this, be careful with the chain rule, would be negative e to the negative x, and y double prime would be, again, a negative and a negative, which makes it positive. So we're going to go ahead and plug in. So y double prime, that's e to the negative x minus y, which is just e to the negative x equals 0. And it's pretty much the same scenario. I'm going to add it to the right side. But it's left-hand side equals right-hand side. So therefore a solution. Okay, so we have C and D here. Why don't you guys do the same thing? Pause the video and go ahead and try out C and D. Okay, welcome back. Hopefully you did examples C and D. And so for C, you gotta be careful with the chain rule with the negative exponent. But if you plug in the second derivative in y, you should get a solution. Okay, and for D, this one was pretty trivial, just zeros all around, and so it is a solution. So that's pretty strange. We got four possible solutions that we know of to the second order differential equation. So four possible solutions to y double prime minus y equals 0. So let's write that out. Here, we found four possible solutions to the second order differential equation, but we really only found two. We really only found two solutions. How was that? So in example A, we found that A equals x, e to the x is a solution. Okay. Then in example B, we found e to the negative x is a solution. And then in example C, we found 10 e to the x minus 3 to the e to the negative x is also a solution. But in reality, this solution from example C is actually what's called a linear combination of the two solutions from A and B. So this is just a solution of a form of like some constant C1 akin to the constant 10 e to the x plus C2 e to the negative x. It's just a linear combination of the two solutions from A and B. So it's not really a third new solution, it's just a combination of the two solutions that we know. And for example, if we bring this back to example D, where you're asking, well, why is y equals 0 a solution? Well, that could be a possible trivial solution because what if zeros were my constant? What if it was like y equals 0 e to the x plus c plus 0 e to the negative x? Well, that's going to give me y equals 0. It's still a possible solution. It's a trivial solution. And it's also a linear combination of our solutions from A and B. So really didn't find four solutions. We really only found two. And that's because for second order linear differential equations, we would only get two families of solutions. Not three, not four, not one. We always get two solutions. And then we could form any type of linear combination that we can see fit. Okay, so that's a little bit of preliminary theory for how second order differential equations have their solutions. We're going to get into more preliminary theory, but that's it for this video, and I'll see you in the next one.